Okay, so welcome back. So the talk in the post-tea session would be given by my colleague, Professor Rahul Siddharthan, who is a professor at this institute. So Rahul, like me, joined originally as a physicist, and then his bio interest got better of him. So he's now part of the computational biology group, where he works on regulatory genomics, among other things. He's also one of the foremost experts of India on machine learning. So without further ado, let me invite my colleague, Professor Rahul Siddharthan, to speak on language models, Markov chains, hidden Markov models, and profiles.
Thanks very much, Sita bro. And I hate to start on a contradictory note, but I am a complete beginner in machine learning. Um, and I'm also not a computational linguist. It's a sibling field, literally in the sense that my brother is a computational linguist. But anyway, so these are techniques that I'm talking about that are commonly used in the areas I work in, which is mainly bioinformatics, computational biology, but they originated in the field of linguistics, broadly speaking. They could be used for epigraphy and other things, probably. I actually had no idea where to pitch this talk, so I'm going to start with some basics of probability theory, which will be required, and then I'll go on to language models and Markov models and so on. Sorry. Yeah. So the first question, since we'd like to be kind of interactive, what is a probability? And in particular, okay, let's pause with this. What does it mean to say the probability of getting heads in a coin toss is 0.5? We make such statements all the time, right? And so most of you will say if you toss the coin many, many times, then roughly half of them will be heads and half will be tails. Very good. So now what is the probability? You often see in the weather forecast 30% probability of rain or 5% probability of rain or so on. So what does this mean? If you replay today's weather conditions again and again, will you get rain 30% of the time? Or you could ask, what's the probability of the same government being re-elected this year? Many TV pundits might say 80%, but how do they know that? Are they going to replace the election? Or what's the probability of life on Mars? I mean, how do you quantify these things? So basically, this one is usually calculated in what's called the frequentist way, which is exactly what I said. You do it many, many times, and it's a number of outcomes you favor over the total number. So that's the kind of frequentist view. But probabilities are used in a much wider context, and historically also it originated in the context of betting and horse racing and so on, where you do want to make a good prediction, otherwise you lose money on it. So a probability is basically a measure of how likely it is that a proposition is true. So 80% means more likely than 70% and so on. And conventionally the measure is between 0 and 1, so 0 means it absolutely cannot happen, 1 means it's certain to happen. This would be the frequentist definition. It's the number of occurrences in a large number of independent identically distributed trials. These are the important words, so I'm sorry if you know most of this, but let's lay down the terminology. Independent means one trial does not affect another trial. So if you're tossing the coin, it doesn't fall and get chipped and therefore affect the probability of the next toss. It remains the same. Identically distributed, again, means that each trial has the same distribution. So again, if it's not a coin, but it's some other event, you don't know the probability of it, but it doesn't change from trial to trial. So that's the frequentist definition. And of course, if you're talking about, let's say, India beating Australia in a cricket match, neither of these two is true. The cricket matches are neither independent nor identically distributed, but people still lay bets on them and so on. And so the frequentist definition is sort of very limited, and the Bayesian definition is actually historically the older one, and it's also called subjective probability these days, and there's a very good book by Janes that goes into it further. It's basically, it quantifies your degree of belief, but the point is, in the Bayesian view, you can put priors on your beliefs, and then you can use data to manipulate them to get posteriors, and those things actually work out exactly the same as in the frequentist probability view. So I won't go very much into this, except very, parenthetically. But let's go over some basic definitions of probability theory. So one is conditional probability, and this is the probability of A given that B has occurred. And it's written, that's how it's usually written. And for example, the probability of rain given that it is cloudy or given that the humidity is 80%. A joint probability is the probability of both A and B occurring. And this is a fairly, it is a fundamental rule of probability theory, which is why I'm bringing it up. It's the factorization of a joint probability can be written in terms of conditional probabilities in two ways. And basically what this is saying is the probability of both of these occurring can be seen as the probability of B occurring and the probability of A occurring given that B has occurred. So a product is like the logical AND, a sum is like a logical OR. And this is another fundamental rule in probability theory, that the probability of A or B occurring is given by the sum of the two probabilities minus the joint probability. So this I won't bother with. And then the last word that we use sometimes is likelihood, which is often you're dealing with hypotheses and data. And so the hypothesis could be a model. For example, it could be a language model. The data could be, for example, sequence, a string or something. And the likelihood is the probability of a hypothesis given the observed data. It's called the likelihood of the data. It's kind of inverted. And with that, we'll move on to sequences. So as I said, I'm going to be talking about sequence models in a broad sense, of which languages are one example. So in biology, you have a variety of different sequences. It could be DNA, where you have A, C, G, T as the 4 nucleotides. It could be RNA, where it is A, C, G, and U as the 4 nucleotides. And it could be proteins, where you have 20 amino acids. You can have language, which can be viewed in the written form as a sequence of symbols. And in this case, the symbols could be the letters of the English language, or it could also be the words. So in computer science, they talk about an alphabet, which is the total collection of symbols you have. And this, in a simple case, you could remove all punctuation and treat every letter as a capital letter, and then you have an alphabet of 27 letters, 26 letters and a space. If you go to the word level, then you'll have thousands of symbols in your alphabet, of course. But both approaches can be used and have been historically used, as I'll say. Sequences occur all over the place. For example, music can be viewed as a sequence. And even though this is Western music, and there are cases where you play multiple notes simultaneously, but you can view this as a kind of a compound symbol. So this is the time axis, and this is the value and duration of the note, basically. And so a lot of things, there are many other kinds of sequences, like you could have, well, so we'll go to that, but what's common to these? So mainly they can be written as a linear sequences of a discrete finite set of symbols, which we call an alphabet, very broadly speaking. They can be very long, and we heard a lot of talks today about large language models where they train it on enormous corpuses of data, which we won't be getting into. Typically, they contain some kind of meaning. And at shorter scales, they contain correlations, but they are not perfectly ordered. They are not completely predictable. And at longer scales, they become uncorrelated. So what I'm saying right now depends on the previous sentence I said. Well, of course, since I'm giving a talk, it does have some order to it. But in a normal conversation, the correlation will die down pretty fast, and more than that. So, and then why do we want to model sequences in a very broad sense? So in biology, you want to understand the function of DNA and protein sequence, and maybe you want to design a synthetic sequence that does some function that you need it to do. And computational linguists, as you've been hearing today, want to create natural language, and these large language models are becoming surprisingly good at that. It also gives you some insight into what goes on when you create the real stuff. If you listen to a computer-generated music Does it really capture you the same way as a real composition does, I mean, by a human? Why and why not, that kind of thing. And there are many other applications. Okay, so with that quick introduction, so here are the basic questions you might have broadly across these fields. Given a model that describes the sequence, you could ask, what is the probability of observing a particular sequence? So we'll write X for the sequence and M for the model, and then this could be written as P of X given M. And this is actually a very basic question. In fact, the definition of a language model is in fact a probability distribution over all possible sequences given some particular, given the model. So, and then another possibility is given a sequence, how do you predict the next element? And this is essentially what ChatGPT and so on do, except they do it in a very, very sophisticated way that I'm not going to talk about. And then the last thing you might want to do, which is pretty important in biology, is given multiple models, how do you choose the more probable model? So you have a sequence of, so let's say, DNA, and it might have many different, so it might be a very long, it might be the human chromosome number 1, which is 250 million base pairs roughly. Some of it codes for genes, some of it is just repetitive sequence, some of it is promoters, enhancers, and so on. So each of these could be modeled with a different model for generating the sequence, and maybe given a new piece of sequence, you want to say, is it a gene, is it a promoter, that kind of thing. And people, in fact, use hidden Markov models, which I'll talk about, to segment the DNA into such functional regions, though I won't talk about that. Okay, so language models. This is the basic definition. It's a probability distribution, P of S over strings, that attempts to reflect how frequently a given string S occurs as a sentence. A sentence is just a set of characters. We are not talking about full stops and things, but, and this is taken from a paper by Chen and Goodman, 1998, which is basically a review of smoothing methods used, which I'll come to, but it's a good enough definition. What is an example of a language model? So the simplest example is a Markov chain. A Markov chain is a sequence of symbols where each symbol depends only on its predecessor or maybe its n predecessors. For example, your sequence of symbols could look like this. Your S is a string of 5 symbols. You could ask, what is the probability of observing this sequence in this order? The order is important. So now what you're asking is P of S1, S2, S3, S4, S5, the joint probability. And you can factorize it by repeatedly applying that factorization rule that we discussed earlier. So this is equal to P of S1 times P of S2, S3, S4, S5 given S1. And then that can in turn be factorized and so on. So finally you end up with this product. And this is a sort of exact answer in the sense, in the mathematical sense. It's also kind of a useless answer because as we'll come to, you need to estimate these probabilities, and it becomes progressively harder as you have more and more conditional things on the right-hand side, which we'll come to. So, but the other thing I want to note is that this factorization actually does not depend on the order. You could equally write P of S3, P of S1 given S3, P of S4 given S1, S3, and so on. Any factorization is mathematically correct. But intuitively, you think a sequence should not depend on things that are too far away. So the typical logical factorization would be that maybe S2 depends on S1, okay, S3 depends on S2, but does it depend on S1? Maybe it does, but so as I said, this full thing is anyway not possible to work with. So this is the simplest approximation. It's called the first order Markov approximation, where each symbol depends on its predecessor, but not on the rest of the sequence. So this is in theory exact, but not useful. This is an approximation, and in theory it's very useful. Why is this more useful? So essentially it's about estimating these guys. So supposing your alphabet is of size 27, which is 26 letters and a space, then to estimate a probability of a letter, you need a corpus many times the size of 27, right? If you want it estimated within 1%, you need 27 times 100, something like that. To estimate this, you will need a corpus of size 27 squared, and then 27 cubed, and so on. So it rises very fast, the size of the corpus you need to train it. And it quickly becomes complicated, and you end up overfitting the model. An example is DNA sequence. A non-functional DNA sequence you might think could be a random string of ACGT. It turns out that they are not equally probable. Typically in most genomes, A and T are more common, C and G are a little less common. But if you assume this model, you find that the probability of AA, AT, TA, TT should all be the same. And that's actually not the case. And so a better model is a Markov chain where you have these conditional distributions where CA might have a different probability from AC or from GC and so on. This still doesn't account for trigrams, and so you can keep making it more complex. And the trade-off is exactly this, that if you have a trigram, you need in this alphabet 64 conditional probabilities, and you need a corpus of that size, many times that size. So, so there's a lot of old computational linguistics literature that's devoted to these things and estimating these high order n-gram probabilities. And this goes all the way back to Shannon in 1948. This is the paper where he laid down what we now call information theory. It's the mathematical theory of communication. But in the early stages of the paper, he talks about approximating English via n-gram models. So this is a zero order approximation, and he did this by hand in 1948 using a single page of some book, counting the number of letters and the number of diagrams and so on, and then generating random text. And if you assume all symbols are equally probable, then this is what he got. If you put in the actual frequencies, but otherwise they are independent, then this is what he gets. Neither of these looks much like English. But once you put in second order, you have some indications that this could possibly be English, so it doesn't really mean anything. And if you put in a third order, you actually reproduce fairly long, not really words, but fragments of words. If you go home and try this on a computer, you'll find that you can go to higher orders, but you'll find that you'll start reproducing large parts of your training corpus all by itself. He also talks about what if you use word approximations. So this is the first order word approximation where the words come independently but with their appropriate frequencies. And this is the second order word approximation. This is what we would call a first order Markov model. Second order is because it's a 2-gram that is using pairs of words. And here fragments of the sentence actually tend to make sense. So this is a great paper to read just for education if you haven't seen it already. And the zero problem is what has taken, so that Chen and Goodman paper I mentioned earlier is focused on this, that if you are training from insufficient data, then a lot of the possible occurrences you will never see. So here is a toy answer. Supposing you have a coin and you don't know upfront that it's fair. So you want to estimate the probability of heads. You toss it, let's say, big n times and see small n heads. What is the probability of seeing heads on the next toss? So for example, you toss it 10 times and you see 7 heads. What's the probability of seeing heads on the next toss? So if it's a regular coin, you will probably say, it'll probably say half, because 7 by 10 is perfectly plausible. So I won't get into that debate. But if you have no idea what the bias of the coin is, and let's say it's not a coin, it is just a process with 2 outcomes, this is your maximum likelihood answer. So your coin could actually be a letter, you could be using a binary alphabet with zeros and ones, and you're trying to estimate the probability of each symbol. So if you have a small data set, you might never see the outcome at all in a finite thing. So supposing you have n is equal to 0, are you sure that 0 is really the answer? It is the answer that maximizes the likelihood of your data, but it's not great. So Laplace gave this rule back in the early 1800s, and it's called Laplace's rule of succession. And the answer is, if you're completely ignorant about the coin's bias, that means this is the probability of heads 0 means you'll never get heads, 1 means you'll always get heads, but the small p for a real coin is at half. But here you don't know what it is, so you have a big P of small p, and it's absolutely flat. If that is one condition, and the other condition is that the trials are independent and identically distributed, then you can prove that this is the correct answer, which I won't have time to do now. Of course, this is not the case for real coins, and but that's so if you're interested in this kind of thing, go and read James's book, is what I'd say. It can be generalized to multinomial or categorical outcomes. If you have L possible symbols that you can observe, and which is usually the case in languages, and in n of observations you observe the ith symbol n sub I times, then this is in fact the generalized Laplace rule. So for example, and this also applies to conditional probabilities. So in your training corpus, you're trying to estimate P of, let's say, E given the previous two letters are TH. That's a reasonable estimate, and often TH is followed by E, so you'd expect this to be kind of high. What you would do is the number of times you see THE plus 1 divided with the number of times you see TH anything plus 27, because 27 in the simplified thing is the size of your alphabet. So that's basically how you would, that's the simplest way you would do smoothing. There are many other approaches to smoothing in the linguistics literature, if you go back and look at it. So much for Markov models. So this is a picture of a Markov model. Basically, it's a set of symbols. So from now on, I'm going to use X for a sequence, and X1, X2, X3, and so on for the individual letters in the sequence. And you have transition probabilities, and it's convenient to have two dummy symbols which are both labeled 0. This is begin, and this is end. And we label both of them 0 just for convenience. So you have to start somewhere, and you have a finite probability of stopping anywhere. So this allows you to create sequences of varying lengths. And these are transition probabilities. So for example, in the English language, you might have a transition probability from A to B and from B to C and so on. So something like Q followed by anything except U might be very unlikely, but and A followed by A is very rare in English, but it's very common in Dutch. So it really depends on your training corpus. So this is a Markov model. Now, a hidden Markov model is a generalization of this, where what you see is not the Markov process. Instead, the Markov states are something that is hidden from you. Sorry. So this is a picture of it. There is a hidden sequence pi, and there's an output sequence x, and x is visible, pi is hidden. And as before, you have transition probabilities from the hidden states, and you have emission probabilities from the hidden states to the output states. And the hidden states could be a completely different alphabet from the output. Typically it is. So it is. So one example where it did come up in linguistics is the hidden state could be a part of speech. It could be a noun or a verb or a pronoun or an adjective or whatever. And the output state is an actual word. So you could have a hidden transition that you start with a noun, and then you go on with a verb, and then you go on with a maybe another noun, and so on. So the ball hit the bat, article, noun, verb, article, noun. And so the hidden states are article, noun, verb, article, noun, and the output states are the ball hit the bat. And then the Markov model would have transition probabilities from noun to verb and emission probabilities from noun to particular nouns. If it is a noun, what's the probability of a particular noun? So it's more sophisticated than that, but that's kind of the idea. So just to explain a little bit more how that works. Okay, so what are the tasks? Typically, you might want to infer the hidden path. In some cases, that's what you want to do. Or you might want, so this is pi and this is x. So Viterbi basically calculates the maximum most probable pi for the given x. X is what you can see. What is the pi that maximizes the joint probability of pi and x? Or you might just want to calculate p of x over any possible pi. And it turns out there are efficient algorithms to do both of those things. So keep in mind that the set of hidden sequences could be very large, because supposing there are k hidden states, k could be 2 or 3 or even larger, and supposing your sequences of length L, then you have k to the power L possible hidden sequences, which is an exponential size, but it turns out you don't have to search that exponential space. But before getting into that, here's a silly example. This is you could imagine a hidden Markov model that generates it, but more realistically, supposing you have DNA, as I said, there are many different kinds of DNA, but we'll just consider coding and non-coding. Coding means it codes for a protein coding gene, non-coding means it doesn't. Supposing that's all we care about, and the difference is the nucleotide densities. Non-coding regions are AC rich and AT rich, and coding regions are GC rich. And this is a possible HMM. Much more sophisticated HMMs are routinely used in segmenting DNA. But in this case, you could think that the hidden states are NNNNN, which is non-coding, then CCC, which is coding, and then again NNN, which is non-coding. A real coding sequence will be much longer than this. But given the output sequence, which is all machine can give you, you want to infer the hidden states, which is NNC. That's the typical task in HMMs. So to illustrate how the algorithms might work, so the most probable path is given by something called the Viterbi algorithm. And basically the idea is you're trying to calculate, so you can calculate the joint likelihood P of x and pi as this product of all the transitions and emissions for the actual hidden and visible states. So this requires you to have both the sequence and the set of hidden states, and then it's just you transition and then multiply all the possible transitions and emissions, and that's what you get. But you don't know pi. So what you want is the most probable pi, which is the that pi which maximizes this. How would you do that? And as I said, it's an exponential space, but it turns out you can do it in essentially linear time. And here's an illustration. So supposing this is your system, that there's a sequence of coin tosses, but there are two kinds of coins. One coin is fair and the other coin is biased. And the fair coin tosses 50-50 heads and tails, but the biased coin tosses 80% heads. And the person who's giving you the sequence flips randomly between the two coins. After each toss, the player keeps the same coin with 80% probability, or flips to the other with 15%, or ends the game with 0.05%. Also, they start with the fair coin with a probability of 0.8. So that gives you P of, so A0 F is equal to 0.8, AFF is equal to 0.8, and so on. I mean, all these numbers in these A matrices you can read out from this. Then you ask, what is the most probable hidden path? And sorry, I think I didn't proofread this correctly, but okay, basically the idea is you can define a matrix which is called the Viterbi matrix. It is the most probable path, probability of the most probable path up until state I. So here the I is on this axis, and the hidden possible hidden states are on this axis. So the at the actual visible states that you see are here. And so you initialize this as V00 is 1, because the initial state is the start state, which has a value 0, and there are no symbols emitted up until that point. And then you can calculate each successive element as the transition from the previous, you maximize this over the values of the previous case. So supposing I want to calculate this, which is the probability of the sequence up until here, HETH, given that the coin was biased here. So I have to compare, it could have come from a biased coin here, or it could have come from a fair coin here. I compare those two possibilities and pick whichever is bigger. And so I can fill out the matrix starting from the top like this, But each time I fill an element, I have to compare two numbers. It could have come from here, compare from here. I pick the bigger one and I put an arrow indicating where it came from, a pointer. And so I fill out the entire matrix until I reach the bottom row. And then I see which is the largest element here. So this is the probability of the full sequence if it was fair. This is the probability of the full sequence if it was biased. So this is larger. So I pick this and then I backtrace through the arrows. And that tells me the hidden states. So the hidden states were that the first three are fair and the rest of it is biased coin. That's the prediction. This is the most probable path. It doesn't mean it's true. But it's in large sequences, so it's often good enough. You're predicting coding or non-coding and you miss the boundary a little bit. Maybe it fits. This was still a fair coin and it flipped to the biased coin here. That's possible. So it doesn't actually matter in practice. So that's one example of HMMs. You can do better than this, in fact. So you might want to ask what's the likelihood of the sequence no matter what the hidden path is. And this is exactly what a language model needs, right? What's the probability of seeing some sequence of letters? Not given a hidden path or not given a most probable hidden path, but overall possible hidden paths. And even though this is an exponential sum, you can actually do it in the same way. This is called dynamic programming. So essentially, you define this forward matrix as the probability of the sequence from the first to the ith element, given that the hidden state pi sub I is k. So it's probability of x1, x2, x2, 3 dot dot till x sub I, given the hidden state is k. Now, if you know this, then you can get the next one, the f sub L I plus 1 is simply the emission probability of the I plus 1 element times all possible transitions from the previous one to this guy, because the previous element hidden state could be anything. You have to sum them because you are summing over all the paths. And then there's a termination criterion, which is this. So the P of x can be written in terms of the last two, the last hidden states you get times their probability of ending summed over all k. And it turns out you can do this from the other end. So if this is called the backward algorithm, you can define b sub ki as the probability of all the sequence from I plus 1 till the n, given that the hidden state at I is k. And then exactly the same thing works, except you start from k is equal to n and you work backwards, and p of x ends up being this. And it's even better if you calculate f of k, the f and b matrices, you can ask what is the probability of a particular hidden state pi sub I, which then is given by basically this. So going back to the Viterbi slide, we said this is predicting that the hidden state here is biased, but that's a hard prediction. This is the maximum maximizing value, but what is the probability that it was biased? You can actually calculate that from the forward backward algorithm expression, and it will probably give you an answer which is not very much greater than half in this case. And this kind of thing has applications to, for example, inferring missing symbols. And so supposing you have a corpus of text and one letter is missing, you want to maybe predict the hidden state there and then scan over the outputs. That's one way to do it. So as I said, my own expertise in all this is basically from the biology side, but these days the AI kind of thing, the deep learning has really taken over the whole field of language models. But I suspect there is still some role for old-fashioned HMMs and things. And in fact, there is continuing work. There is some work on combining HMMs with transformers and so on. But throughout the last 20, 30 years, there have been papers on text recognition, handwriting recognition, and so on using HMMs. And this was actually probably one of the methods of choice until deep learning came along. But going forward, it might be something that can be combined with deep learning. Okay, so I've been kind of talking without any questions. So before I go on, maybe any questions at this point? Okay, so the last thing I want to talk about is something called profile HMMs, and I don't know if there is any application to that in linguistics or epigraphy and so on, but Sitapra was saying, so this is an example of a sequence alignment of 7 protein sequences. So ignore the rows 1 and the last row. The ones in between are drawn from the alphabet of amino acids, which has 20 letters in it. Sorry. And what this means is, in this case, that the things that are vertically aligned are likely to have evolved from a common ancestor. They are homologous. And the dashes are where either something got deleted, meaning there is a common ancestor that all of these came from. But as DNA evolves and protein evolves with it, it could get mutated, which means you will replace an amino acid with another, or sometimes you won't. Sometimes the amino acid stays the same. Or you could have an insertion, meaning you had the sequence ancestrally, you had this also, but you got this thing inserted in the middle. Or you could have a deletion, meaning most of the other sequences have something and you see this guy has nothing here. Then it's reasonable to think that this might have been deleted. Similarly, this is probably a deletion in these two sequences. So, and everything else is called a match. And now the question is, given a set of protein sequences from a common family, these are all globin proteins, how would you check whether a new sequence that you get, how likely is it that it came from the same family? So what is P of X given some model that describes these? So what kind of model would you use to describe this? And so that's okay. So let's look at a sort of zoom in of just this section of this. A little bit wider. So it's basically that part of it, just for simplicity, and see in detail how we might do this. So as I said, when you see something missing, it could either be because it got lost or because the other sequence had something inserted. So if you just had these two sequences and you saw this gap here, you don't know whether it's because this got added in or this got taken away. But when you see that out of 7 sequences, only this guy has these 2 letters, then it's reasonable to assert that this is an insertion and this is a deletion from. So we are going to treat it like that. So the stars here indicate match states. So that's saying that it matches with some ancestral amino acid. You don't know what it is. But any output sequence that lands up here should be matching. And so let's start with just match state. Supposing you don't have any insertions, deletions, you just have a sequence of amino acids in each thing, and they're all lined up. Can you model that with a hidden Markov model? This is kind of a trivial HMM. So what's not shown here is the emission probabilities. So let me draw those explicitly. L is the length of the sequence, let's say. So what it's saying is your first column here is M1, then it's M2, M3, so there'll be 8 match columns like that. I would only drawn 3 here, but imagine a dot, dot, dot. So each column, so you have transitions from one column to another, and then each column has an output distribution of amino acids. So given that you are at this position, what are the probabilities of the different amino acids? And that you do by counting what you actually see there and adding a pseudo count and whatever. So what this is called as a profile, meaning it's site-wise multinomial distribution over the same alphabet. So the first position has a lot of V's, the second position is kind of mixed up. Let's say so it goes. So the 6th position has 2 V's and Y. So for a protein chemist, they'll probably see similarities there between certain of these things, but we are just modeling it probabilistically. So this is a very trivial HMM where from the beginning you can only go to state M1. From M1 you can only go to M2. From M2 you can only go to M3. So it's actually a completely deterministic hidden path. Only the outputs are probabilistic. But of course we want to do better because the real alignment does not just have match states. It has insertions and it has deletions. So how do you model those? So we'll talk about deletions first. The idea is that you could have states which are silent and don't emit anything, and you could go from a match state or from the begin state either to the next match state or to the next delete state. So this would be M1, this would be D1, and this, if this is ML, this is DL. And so you would be able to model, for example, this sequence as saying you went from match M1 to D2 to D3, which don't emit anything, and then you match the rest, M4, M5, M6, M7, and M8. That would be the hidden path for this. It need not be, because you could also try matching M1, M2, M3, M4, M5, and then deleting the rest. So you'll see all possible hidden paths and which one is most probable. So that's how you do delete states. And how do you do inserts? So you can think of another state which they represent by a rhombus here, and the idea is that from begin or from any match state you can go to an insert state where you keep inserting nucleotides. So in this case you will go from M1 to M2 to M3, and then you'll go to I3. So let's say this is I3. So from M3 you go to I3, and then you can stay in I3 at least once or as many times as you like. Typically inserts tend to be kind of long. So then so you'll have a path that goes from M1, M2, M3, I3, I3, and then you go to M4, which is the next match state, and then you go through the remaining match states. You could have some combination of insertions and deletions, which this example is too small to give, but so essentially this gives you the architecture of a profile HMM. This sort of backbone of it is the match states, and if there was nothing else, then it would just be a deterministic march through these. But you could have a deletion from what matches the ancestor. You could have an insertion that wasn't there, and these other states help you do that. And then given a new sequence, you can ask what's the most probable path of hidden states that explains your new sequence. And that path will then help you align your new sequence with the alignment that you already have. You align, if the hidden state is a match state, you align it under the appropriate M column. If it is an insert state, then you insert gaps and everything else and make space for this. If it's a delete state, you just put a dash where it is and move on. And that's essentially how they do. So the authors of this book actually are authors of a software called Hummer, which is a sophisticated profile HMM program to align protein sequences to families of proteins. And it's very efficient and very fast and widely used. Does this have any relevance to the topic of this conference? I don't know, but Siddhartha was telling me that it's of interest to look at concordances where certain words are sort of lined up with each other and contexts and so on. And maybe there is some analogous version of this might be applicable in modeling scripts or modeling languages. Okay, anyway, so if you train the HMM on this, this might be an example of your trained HMM on the actual sequence there, where the thickness of these arrows indicate how probable particular transitions are. For example, this is, you don't have any examples of inserts right at the beginning, so these inserts are very thin. But you do have inserts, one case of an insert after 3. So if you look closely, this arrow is a bit darker than the other insert arrows. And similarly, they haven't drawn they haven't drawn this arrow, for example, which exists. But anyway, so that's probably too much material for a 45-minute talk, but I hope some of it was interesting. So yeah, thanks very much.
Thanks, Rahul. Questions?
Yeah, okay.
So in biological sequences, you see this hierarchy of you start with ACGT and then you go to these three codon amino acids, right? And these amino acids make proteins. So do you think you can think of something like that for languages as well? Like alphabets creating words, but the words are way too numerous in number in this case. But then words stringing up together to make sentences, which are meaningful functional elements.
Right. So the codon thing is kind of an extreme case because the codon consists of exactly three nucleotides.
Right.
And three nucleotides code for one amino acid, but there's a lot of redundancy there. So it's as if you can spell the same amino acid in up to 6 different ways because there are 6 codons that code for it. So I can't offhand think of an, of course there are very sophisticated programs to predict genes which use this codon property. So what I showed you was a very trivial example, but any serious program will take account of this unit of 3 business. In languages, you have words of many different lengths, and you have so the rules are just much more complicated. So
Right.
I don't know whether there's an exact analogy there.
So, in continuing on what I was telling you, the idea that multiple sequence alignment could have something to, say to epigraphy is because I remember Mahadevan, when he was preparing his Indus corpus, he had this thing about whether certain signs are just variant signs of each other or are they distinct signs. So there was this big debate that whether a diamond inscribed with a square and a oval inscribed with a square is the same sign or different signs, whether they're just stylistic variations and so on. So it turns out that if you actually do a sequence alignment where you look at all sequences where these two signs occur and align them, it turns out that whatever occurs to in the neighborhood of these two signs are very times same.
Right.
Which suggests that maybe either they're of the same class and or maybe they're actually the same sign, they're just stylistic variations. And so occasionally these kinds of things led us to believe that maybe doing something like multiple sequence alignment using algorithmic technique. See, these are all done manually.
Right.
So might be useful to epigraphy.
So this might be more an example of where you could apply a Markov model. So supposing you had you were new to English and you didn't realize that this and this are really the same letter.
Correct.
And so you treated them as 2 different letters.
Yes.
And you develop a Markov model with 27 letters plus space.
Right.
And then you might find that transitions from this to other letters or this to other letters are basically the same. And then you might be able to infer that maybe, so I don't know, I haven't thought about this much, but there may be some such thing you could do.
Sure.
Just for simplicity, because let's throw out the spaces and dashes and commas, and not throw out the spaces. Spaces are there. Throw out the full stops, commas, dashes, question marks, just to keep life a little simple. But of course, ChatGPT doesn't do that. It understands punctuation.
Okay, so if there are no further questions, let's thank Rahul once more. Okay, so after a 10-minute break in which you can, go out and stretch your legs or something, we can start with the tutorial. So the tutorial has, a couple of handouts. I will give this handout to you, and then we'll try to see, what we do when we actually encounter, something which we can't make sense of. What are the possible strategies? It's just a fun game. Okay, so just think of it as a way of, stretching yourself and so on. So it's more of an interactive thing. Okay. So please come back here in 10 minutes.